And now let's go over our second practice problem. So in the second practice problem, let's apply a neural network to a different scenario, predicting the energy consumption of a building based on historical usage data. So we are building a neural network. Predicting the building energy consumption. And as we know, a neural network typically has three groups of layers. We have the input layer, we have one or more hidden layers, which is where the training happens. Then we have the output layer, which gives us our output. The training happening inside of the layers, conducted by activation functions. And then the output layer is always calculated with back propagation. Which is always typically calculated with gradient descent. And we would have a mean loss function. A loss function. Let me just clean this part up. There we go. The loss function serves as a purpose to compare the accuracy of training. And so, now that we have already, one second, zoom out of here. Just fix this up. Okay, there we go. And so the steps that we need to do to be able to actually build out our neural network are going to be the following. So one, we always focus on pre-processing the data. Where the first step still remains the same as a previous practice problem, but in the context for energy consumption prediction, this involves normalizing the historical data. So normalize historical data. And weather conditions as well. to ensure the network receives this information in a format it can efficiently process. So that means everything needs to be numerically formatted. And this step helps the model accurately capture the influence of external factors like temperature and humidity on energy usage, since we have already ensured that the network receives this information in a format it can efficiently process. And the second step that we have is the network architecture. This is the part where we ask ourselves how many layers would we use in this case to be able to train, and how many epochs would be laid out in order for the training to actually be commenced. So the complexity of this problem dictates the architecture. So revolves around the complexity for the architecture. For energy protection, a similar two-layer design could be used. So in this case, we're doing a binary classification. So we can do 2 layers, with the first layer focusing on the immediate factors, so we're doing binary classification. We have 2 layers. So the first layer, I don't know why it does that. So we have 2 layers. So the first layer will be focused on the immediate. Factors such as weather conditions, well, the second step, or the second layer, will be focusing on the complex long-term trends like seasonal changes. So long-term. Something that has to be predictable. And the design must be balanced with depth, referring to the number of layers, and breadth, number of neurons. So depth refers to number of layers. Breadth, number of neurons. And in order to capture the nuanced relationship between weather conditions and energy without overfitting, we're trying to mitigate overfitting. So mitigate overfitting data, which would give us inaccurate predictions if we were to not properly assess. So, and then the third step that we would have to do is going to be focusing on training the network. And while training the neural network, the steps involve adjusting the model to minimize the error between its predictions and actual energy usage. We do this with activation functions and backpropagation. With activation functions and backpropagation. Typically that will involve gradient descent in just that case. This might involve allowing the model to be able to learn how different factors contribute to energy usage and refine its predictions over successive training epochs. So there will be successive adjustments throughout each epochs. And this iterative process allows the network to uncover the intricate patterns linking weather conditions and historical usage to future trends. So we are linking in the present weather conditions from historical data. To create future predictions. Let's be able to outline and illustrate. Then the next part that we need for step 4 is going to be evaluation and assessment. And so throughout the step, we just evaluate the model's performance against an unseen data to ensure it's generalized well to new situations. So we have a validation data set. And it could be just completely something that can be from database, can be from anywhere. But the point is that it's untrained / not part of the trained data. And it's generalized for new situations. New situations. For energy consumption prediction, this might involve using data from a different time period or a different building to test the model's accuracy. So if I were to put an example, in this case, energy consumption from a different time period. Or different building. And or with different energy consumption. And finally, we all know step 5, when it comes to machine learning or deep learning models that are also made, the investors love this. It's deploy, deploy, deploy. Final step is to integrate the trained model into a building management system. So that would just be depending on what context you want to put it, you can put it in cloud for other model platforms, but in this case, we're just going to put it in building management system. And it always depends on the context of your application. And where the following model is built and designed to predict energy needs in real time, continuous monitoring and periodic retraining with new data as usual. So train with new updated data. / updated data. Continuously and monitored. Because we always want to maintain accuracy over time. Go. And so let's just go over. Let me just move out here. Going over our following script. So after we import the following necessary libraries, we then begin pre-processing the data in the following format. So we have our CSV file, and then we also select features which are considered relevant for predicting energy consumption as well. We have temperature, humidity, and time of the year. And then we have the target variable, which is what we want to predict, in this case, which is going to be energy consumption. And then what we do is that we initialize the min-max scaler to scale features / targets on the range between 0 and 1, since we're doing a binary classification. And then we compute the min and max values for scaling features and store them in the following parameter as well. And we compute the min and max values for scaling the target and store the parameters as well. And we do an 80-20 split for when we are about to train the following model, hence the 0.8 over here. And we ultimately determine that the parameters are able to derive from the training set to prevent information that is being leaked from the test set. So we already set this up between the training amount size and the features we're trying to extract and the actual value that we want. And so what we will be doing is that this is where the neural network architecture is, and what we're doing is that we are actually using a dense, we're using a sequential model with 3 different dense layers, namely with 64 neurons each. And then each input layer, for instance in this one, will have 64 neurons and ReLU activation to shape the matches for the number of features. Then we have the hidden layer with 64 neurons and ReLU activation for nonlinear feature extraction, which we already have for following features up here that we defined. And then we would output, have the output layer with the single neuron for regression output. And then what we do afterwards is then we compile the model all together, but we're actually using a tool called the Atom Optimizer to be able to compile the model within the 3 different layers that we have, and then present a loss function for the mean squared error. Then finally, after we've already built the architecture for our neural net, we'll then train the model on the training data based on 100 epochs with a batch size of 32 for the entire data set, and then we split the following data set for validation as well. We then make predictions on the test set and invert the scaling on the prediction to transform back to the original scale. And then finally get our output for energy consumption. And so, yes, this was our first lecture for our Foundations in Deep Learning series, focusing on neural networks. Thank you again for taking time to watch this. If you found this video helpful, be sure and feel free to like and subscribe. And if you have any other questions as well about what we just went over, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.